La 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 la. La 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 la. La 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 la. La 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 la.
Here in this video, we would like to solve a problem. The problem is like this. A battery is first connected to an external resistance R1. What do you mean by that? Let me try to draw a diagram. There is a battery whose EMF is E, having some internal resistance. It is then connected to a external resistance R1. When it is connected that way, it has generated some heat. How much heat is generated? I need to write a formula. You know the definition of potential? Amount of work done in bringing a unit positive charge from infinite distance up to a point, W by Q. So work done can be written like VQ. You know the definition of current, rate of flow of charge, I equal to Q by T. So Q can be written like IT. In the place of V, using the Ohm's law, I can write IR and IT. So the work done is further generated like heat, which is also called like a Joule's effect. So heat generated is I square RT. So as the resistance is R1, let me call that heat generated as I square R1T, right? I square R1T. But of course that I value also will vary. So I will call that I as I1. How much is that I? I can write a formula using the Ohm's law. I is equal to total EMF by total resistance. Total EMF is E. Total resistance is R1 plus R, because this internal resistance always acts like a series resistance and current goes like this. So heat generated H1 in this case is equal to I1 square, that means E by R1 plus R whole square, R1 into T. Now it is given in the problem that at the same time another external resistance R2 is connected and the heat dissipated in both the cases is same. So if you imagine, if R2 is connected to the same battery, the heat generated in that case, I can write it like H2 as I square RT. I is EMF by resistance, but in the place of this R1, imagine a R2. So I shall write R2 by R whole square, R2 and C. It is given in the problem that H1 equal to H2. If that is the case, what is the value of this internal resistance? That's the question is, in terms of two external resistances. So I got H1 value, I got H2 value. I can just equate both of them. Let's equate. What happens in that case? H1 is equal to H2. H1 is this. What is that? E by R1 plus R whole square, R1 and T. This is H2. E R2 plus R whole square, R2 and T. These times are same, given in the problem gets cancels. This E also gets cancels because it's the same battery. So what is remaining? R1 by R1 plus R whole square. Here whole square is there. R2 by R2 plus R whole square. So if you simplify, R1 by R2 equal to R1 plus R2, R1 plus R by R2 plus R whole square. Let's the binomial expansion of this has to be done using the formula A plus B whole square equal to A square plus B square plus 2AB. So let's do that. That implies what happens. From here we are continuing. From here, R1 by R2 is equal to R1 plus R whole square is R1 square plus R square plus 2AB, 2R1R by R2 plus R whole square means R2 square plus R square plus 2R2R. Let's cross multiply both of them. What happens? First let's multiply with this R2. R1 square R2. Each term of this R2 has to be multiplied with each of this in the numerator. R2 R square and then this term with this term. 2R1 R2 R is equal to. Now let's multiply with this R1 with each of these terms. What happens? R1 into R2 square. R1 into small r square. R1 into 2 R2 and R. You can see 2 R2 and R, 2 R2 and R same in both the equations. They can be gets cancelled. So what's remaining? What's remaining is this. R1 square R2 plus R2 small r square equal to R1 R2 square plus R1 R square. Let's rearrange the terms. Get this term to the other side, this side. What happens then? R1 square R2 minus R1 R2 square equal to R1 small r square. Let's take this also to the other side. Minus R2 small r square. Let us take small r square common. R1 minus R2 of small r square. Let us take here R1 R2 common in both the terms. Here one R1 will be remaining, here one R2 will be remaining. This R1 minus R2, this R1 minus R2 cancel. So what is finally remaining? R1 R2 equal to small r square. That implies small r equal to square root of R1 and R2. So if that has to happen, the condition is internal resistance of that cell must be equal to square root of product of external resistance of the first case with the external resistance of the second case. This is how we have to solve. To solve this problem, we need to know the basic concepts like the formula of the heat. We have already discussed this. That's the only formula that we need to know to solve this problem. That's it. Thank you for watching.